Okay, let's talk about finding the leading correction to the partition function for a quantum system described by a particular Hamiltonian. So here's the problem we're tackling. We have a quantum system and its behavior is governed by this Hamiltonian, which is given by h equals j times sz plus lambda times sx. Now Si is defined as h bar over 2 times sigma I, where sigma I are the well-known Pauli matrices for I being x, y, and z. The important condition here is that lambda is much smaller than j and both are greater than 0. Our goal is to figure out the main correction or the leading correction to the system's partition function due to the small lambda term assuming a temperature T. Alright, step 1 is to get our Hamiltonian into a clear matrix form. We know the Pauli matrices for x, y, and z. Sigma x is the matrix 0, 1, 1, 0. Sigma y is 0 iota, iota 0. And sigma z is 1, 0, 0, 0 Mentos. We are given h equals j sz plus lambda sx. We substitute the definitions of sz and sx using the Pauli matrices. So h becomes j times h bar over 2 sigma z plus lambda times h bar over 2 sigma x. We can factor out h bar over 2, leaving us with h bar over 2 times j sigma z plus lambda sigma x. Now, plugging in the matrices for sigma z and sigma x, we get h bar over 2 times j times the sigma z matrix plus lambda times the sigma x matrix. Multiplying those in and adding them together gives us the matrix form of the Hamiltonian h bar over 2 times the matrix j lambda, lambda j. Step 2 is to calculate the eigenvalues of the Hamiltonian. We need these eigenvalues to find the partition function. To find them, we solve the characteristic equation, which is the determinant of h minus e times the identity matrix set equal to 0. As shown, we take our h matrix and subtract e along the diagonal. We then calculate the determinant by multiplying the diagonal elements and subtracting the product of the off-diagonal elements, setting the result to 0. Expanding this equation, we rearrange the terms to solve for e squared. Factoring out the common term, we arrive at the expression for e squared. Finally, taking the square root, we find the true eigenvalues are plus or minus h bar over 2 times the square root of j squared plus lambda squared. Step 3 is crucial because we use the condition that lambda is much smaller than j to approximate the eigenvalues. Starting with the exact expression for the eigenvalues, because lambda is much smaller than j, we can factor out j squared from inside the square root. Next, since lambda over j is small, we can use the Taylor expansion for the square root of 1 plus x, where x is lambda over j squared. Substituting this expansion back into the eigenvalue expression gives us the expanded form shown on the slide. Distributing the terms, we arrive at the expression on the following line. Finally, for the leading correction, we keep only the terms up to lambda squared to obtain our two approximate eigenvalues, E1 and E2. Step 4 is where we calculate the partition function, usually denoted by z. The partition function is the sum over all possible states of e to the power of minus beta times the energy of that state, where beta is equal to 1 over kBt. For our two-state system with eigenvalues E1 and E2, the partition function z is e to the power of minus beta E1 plus e to the power of minus beta E2. Substituting our approximate eigenvalues E1 and E2 from the previous step, we get z equals e to the power of minus beta times h bar j over 2 plus h bar lambda squared over 4j plus e to the power of minus beta times minus h bar j over 2 minus h bar lambda squared over 4j. We can rewrite the exponents by separating the terms. This gives us z equals e to the power of minus beta h bar j over 2 times e to the power of minus beta h bar lambda squared over 4j plus e to the power of beta h bar j over 2 times e to the power of beta h bar lambda squared over 4j. Continuing with step 4, we apply another approximation. Because lambda is small, the term involving lambda squared is also small. This allows us to use the approximation that e to the power of y is roughly 1 plus y for small y. We apply this to the exponential terms within the brackets. Next, we substitute these approximations back into our expression for z. Finally, we multiply out the terms as shown here. Continuing step 4, we group the terms in our approximate expression for z, separating those without lambda squared from those that include it. This gives us the expression shown for z. Now, recall the definitions of hyperbolic cosine and hyperbolic sine. Using these definitions, we can substitute into our expression for z. Simplifying this further, we get the final approximate expression for z shown here. The first term in this expression is actually the partition function for the case where lambda is 0. We call this the unperturbed partition function z0. The second term is the correction to z due to the small lambda. This is the leading correction, delta z. So the leading correction, delta z, is simply this second term. Finally, step 5 is to substitute the definition of beta back into our expression for the leading correction. Remember, beta is 1 over kBt, where kb is Boltzmann's constant and T is the temperature. Our leading correction delta Z is beta h bar lambda squared over 2j times sin hyperbola of beta h bar j over 2. Replacing beta with 1 over kBt, we get delta Z equals 1 over kBt times h bar lambda squared over 2j times sin hyperbola of h bar j over 2 kBt. Rearranging the terms a little bit for clarity, the leading correction delta Z is equal to h bar lambda squared divided by 2j kBt, all multiplied by the hyperbolic sign of j h bar divided by 2 kBt. And there you have it. The leading correction to the partition function for this quantum system for small lambda compared to j is h bar lambda squared over 2 jkbt times the hyperbolic sign of jh bar over 2 kbt. This is the main deviation from the simple case where lambda is 0.